let's start with the seminar for this week. This time will be Pavel Stránský from Czech Republic, from Prague, from Charles University, speaking about excited state quantum phase transitions in the continuum. So Pavel Stránský is part of the Czech gang, let's say, or Czech team on ESQPTs, and I knew him a long time ago, in I don't know now how many years, but he got his PhD in the Charles University under the supervision of Pavel Vigner, and then he went as a postdoc to the Instituto de Ciencias Nucleares, same place where I did part of my thesis, and we met there briefly, and then after a postdoc there, he went to Italy, to the ECT STAR, still as a postdoc. Then he went back to Mexico, getting his first position there in the UNAM. And then from UNAM, he moved back to the Czech Republic, where now he's a professor there. He's going to speak about excited state quantum phase transitions in the continuum. So we're moving from discrete states to the continuum realm, where states are not anymore discrete, are not bounded, problems are not bounded. And I think this is going to open a completely new perspective on ESQPTs, and a very, very interesting ones. So thank you very much, Pavel, for joining us today and for giving us this seminar that I'm sure it will be very, very interesting.
So thank you very much for the introduction, Kuro. Also, thank you, and thanks Jose Enrique for organizing this nice series of seminars. It's great that we can gather despite all these problems with the pandemic of COVID. So I'm very happy to give this seminar. As Kuro mentioned, I will talk about the ESQPTs in the continuum. I added also the subtitle about quantum tunneling, because it will deal a lot about this phenomenon. So this work has been done in collaboration with Pavel Vigner and Milan Šindelka, who is a member of the Institute of Plasma Physics of the Czech Academy of Sciences, and Michal Klotz, who is he is now on postdoc position in Basel, the university, but as I heard, he is moving from physics towards something more related with medicine. So he got a job there at in hospital. So he will work in hospital. This work has been published already. So we wrote a paper, a letter that was published a year ago, and then we extended the work and submitted it to Physical Review A. Okay, so this work was supported financially by the Czech Science Foundation and by the Faculty of Mathematics and Physics. Okay, so the outline of this seminar, I will give you some brief theoretical and also experimental motivation. I will start with a theoretical one because I am a theorist. Then I will give you the theory, which is in fact quite simple, but it's very intertwined. So there are many connected quantities, many connected phenomena. So it will connect actually continuum level density with phase shift and complex time shift, and something like complex time delay in the tunneling phenomenon, and then also with the ESQPT-like singularities in the continuum level density. I will demonstrate it in simple one-dimensional, systems with 1 degree of freedom, and then I will give summary and conclusion. So the theoretical motivation so imagine we have a 1 degree of freedom bound system. So now let's move to the simplest cases that we all know or have heard of. A one-dimensional bound system with 1 degree of freedom. So there is this simple formula between the smooth quantum level density and the period of a classical trajectory at energy E, providing we have some kind of mean field, some classical Hamiltonian, some classical image of the quantum system. This formula can be derived easily. So you take the smooth part for the level density given by this Weyl formula, and then you perform the integration, providing the Hamiltonian has this simple form, and you arrive to this simple expression. So just to remind you, and I will be very brief here because you all know about this stuff, just to show you the results for this simple cusp system, which is just a quartic oscillator plus some linear term depending on a control parameter lambda. So the level dynamics looks like this, and this system changing lambda undergoes a quantum phase transition, ground state quantum phase transition at lambda equals to 0, but also there is this critical triangle where the excited state quantum phase transitions take place. So if you take the level density, the profile of the level density looks like this. So there is a jump of the level density and there is a logarithmic divergence. The jump is connected with the appearance of the additional local minimum in the potential, and the logarithmic divergence is connected with this local maximum there. So you can apply now this formula and you can immediately say, okay, so the period of a classical trajectory here will have some jump. Okay, so now I have to stress that by period of a classical trajectory, I mean now the sum of periods of trajectories in all accessible areas of the Hamiltonian or of the system. So then, because this minimum appears here, so the total time here, this total time increases, suddenly jumps up, and then you reach this maximum. So you know that the trajectory at this point has infinite period because it actually stops at the local maximum. So that's why we observe the logarithmic divergence also in the time, in the period of the trajectory. So that is some kind of review of the ESQPTs in bound system of 1 degree of freedom. So now a question is, so can this formula be extended to continuum states? So imagine we had now a completely different kind of system with 1 degree of freedom, some kind of tunneling system. It can have several like more complicated structures, something like multibarrier tunneling system. So this is a potential, some hypothetic potential. So you take a particle, some modeled by some incoming wave, and you can calculate like different kind of things. For example, the transmission probability or amplitude. You can calculate the phase shift. So now the question is, okay, so what about this formula? Can one introduce an extension of level density into the continuum, and can one connect this extended level density with some kind of period of some trajectory? And what about the effects of the stationary points which induce ESQPT or divergences in the non-analyticities in general in the level density for bound states? So this is the theoretical motivation. So now a couple of words about quantum tunneling, so everybody knows it is just to review the history and the experiments and the physics that or the experiments where the tunneling phenomenon is important. The first of all is the scanning tunneling microscope that okay, it works so in such a way that you put some voltage, so this is a tip of the probe. You have some surface, and then the tip moves very close to the surface, and due to the tunneling phenomenon of electrons from the surface to the tip, you can see that the current changes, and measuring the current, you can measure the distance, because the distance depends, or the current depends on the distance in such a form. The first tunneling microscope was constructed in IBM research laboratory, and there were a Nobel Prize. Two guys won the Nobel Prize in 1986 for inventing the scanning tunneling microscope. So then, okay, the tunneling can be used also for very simple but functional, let's say, description of radioactive alpha decay. So you can take the alpha particle bound in some complicated nucleus in a potential looking like this, and you calculate the probability of the alpha particle that it goes out from the potential, and this probability can estimate the, for example, the half-life of the radioactive nucleus. So then there is this tunnel diode, which is an example of another Nobel Prize. It was actually given before the tunneling microscope Nobel Prize. It was given to Leo Esaki from another company, Sony. And okay, so the tunneling microscope, the tunnel diode has this very funny property that you increase the voltage and then you measure the current, or there is a current going through the diode, and the current at first grows, and then with increasing voltage it goes down. So there is a region of negative resistance. The first part of this curve is connected with tunneling effect. So the band structure there looks like this. So this EC is a conducting band, this EV is a valence band, and the electrons from the conducting band can tunnel through this gap into the valence band. So you have the PN transition like in every semiconductor. So then increasing the voltage, you change the conducting band goes up. So at one point there is no tunneling possible, and so this is in the middle panel. It corresponds to this negative resistance region, and then when you go beyond this valley point, you get just a conventional diode behavior. So it's a tunneling diode. There are like more complicated extensions of this semiconductor. It's called resonant tunneling diode. So instead of like one barrier, you have two barriers here, and changing the voltage, you can arrive at the resonance. So there are some particular voltages in which you get a particle through like some big current there. So this is resonant tunneling diode. You can extend it. So you see that there is a research on multi-layer materials with like multi-barrier kind of potential, and you can actually do the same kind of analysis than in the simple resonant tunneling diode. So another experimental phenomenon that is related with tunneling is the so-called tunneling time. So people are highly interested in the time that, okay, if you put a particle in one well, in a multi-barrier potential with multiple wells in between the barriers, so you can measure the time for the particle to take leaving one of the well, or tunneling through the barrier. So you see that there is a bunch of, this is just some example of papers related to this attosecond science, attosecond metrology, and an attempt to measure this tunneling time. So there are even some very crazy hypotheses that this tunneling time, that the particle can tunnel like faster than light. But okay, I just mentioned it. I don't want to say anything more about this kind of hypothesis. So now let's go to the theory. So we will focus on two quantities, level density, and then later on the time, some kind of time, and we try to connect these two quantities. So I will start with the level density. First of all, and this is not a simple task, we have to extend the level density into the continuum. So what I show here is just the conventional level density for bound states, rewritten in several different forms. So the level density is given by a sum of delta functions. So actually you can expand, you can approximate the delta functions by this Lorentzian functions, where you have to introduce some small parameter epsilon that goes to 0, or you can write the same quantity as this kind of limit, imaginary part of the trace of the green operator. Again, you have to introduce some small imaginary value governed by this epsilon parameter in order to avoid the divergences at the eigenstates at the energies K. So the problem when you want to extend it into continuum, so imagine you take this formula. So one of the way you can do, and one of the way you can calculate the properties of a continuum system is that you suppose, and I will suppose it in the rest of the talk, that the support of the potential is finite. So that the barrier are in some finite part of the space. So I can put this potential into a huge box and calculate this kind of level density, let's say, and then make the box larger and larger and go with the size of the box to infinity. So this one can do, but the problem is that the level density will diverge, because you will have like you will have like a continuum of delta functions. So one has to treat it in a more subtle way, and it has been done. It was done in 1998 and 1999. So instead of taking just an extension of this simple formula into the continuum, you take the extension of the formula, but you subtract the appropriate level density for a free particle. So this would diverge, but, and it can be shown that this difference is a finite, well-behaving function. So, and a nice thing that this quantity contains a lot of information about the scattering process, for example, in the continuum. So this is the extension to the continuum. So now we make another step, and this step is important. So we, instead of taking real energy here, we take a complex energy, which I will denote this script E by the script E, and it's just a difference. So it's I parameterize it in this way. So this normal E corresponds to the real part, and then I have this gamma, which corresponds, which will later can be interpreted as a width of some resonance. So that's why there is this factor I over half. But this is a real part, and this is the imaginary part of the complex energy. And so one can extend this continuum level density into this form, where now this E, the energy, can be complex. So you get the density for the, or okay, you have the level density for your system, and then for the free system you must subtract it again to get a well-behaving quantity. You can write down the real and imaginary part, and you can use some version of this expansion here, so you can approximate the real and the imaginary part. You can approximate. You can exactly write down these fractions as these Lorentzians, okay. So later on, I will show. I will give some. I will interpret some of the energies as resonances. But okay, how now? Now it seems like quite a confusing theory, because what's now this EK and so on. So in the next slide, I will present a method how to deal with the continuum like eigenstate, let's say. So one of the method is the so-called complex scaling method, which is a method known from scattering theory, and it consists in like turning your coordinate and momenta into the complex plane. So basically, the details are given in this inset here. So there is some similarity transformation that is not unitary. So you turn the x and p coordinate operator, you turn the Hamiltonian, and you turn it in such a way that your like scattering states, or the states that are not squared integrable, they become squared integrable. So now the exact procedure is the following. So you take you have your potential. An example is here. You put it in a box. You use this complex scaling method, and you calculate the spectrum of this transformed Hamiltonian. And so what happens? So I have some kind of animation. So there is a parameter theta, and you can change it. And the parameter theta actually has some upper bound, because above the value, which for the kind of potentials I am studying, the value is pi over 4. And so you can tune this parameter. So what happens when you do this procedure? So you see in this figure, so on the horizontal axis, there is the real part of energy. On the vertical axis, there is this width, this gamma, or the imaginary part of the energy. And each point corresponds to one of the states there. And so what you see is that you get a set of discrete states, and then you get this line. So the set of the discrete states are resonances. They can be interpreted as resonances, and they are independent of the angle theta of this complex scaling method, but they are also independent, and that is highly important. They are independent on the box size. And then you have this line. So actually this line is also a set of points, but the points become, the set becomes denser and denser with increasing L. But when you go with L towards infinity, so you make denser and denser just this line, but nothing happens here. So, and then if you take a free system, a free Hamiltonian, you get just this line, because this is just the continuum. It's sometimes called rotated continuum in this kind of, in the scattering, complex scaling method. So now you see that when you take the level density connected with this system and you subtract the level density connected with the free system, so you subtract these two like this line from another line, and what remains is, to some extent but not completely, is the effect of just these resonances. These resonances are not a complete set of resonances, because some of the resonances would be behind this line, but you can't, sometimes because of numerical reasons, sometimes because of this constraint, you can't reveal all the resonances. So the rest of the resonances are somewhat hidden in the rotated continuum, but these resonances are true resonances and they are revealed by this method. So now very briefly about the system size and semi-classical infinite size limit. So we are dealing with this kind of Hamiltonian in this form. So you can introduce some kind of size parameter, as you know from many body systems. So the size parameter here can be identified with this kappa. Okay, so this is not, this has some unit. It's not, it has some unit, but I suppose that the scale of energy and the scale of coordinate is 1, so that then this quantity doesn't have any particular unit, and you can say that it is the size of the system. You can change the size of the system either by increasing the mass or, okay, formally decreasing the size of the Planck constant. And the semi-classical limit is approached when this size of the system goes to infinity. So you see what happens when you change the size of the system in the scaling method. So you see that the number of resonances increases. So actually, when the size of the system, here I change the size of the Planck constant, when it goes to 0, then you get a set of, like a line here. This will be important because for some conclusions, one has to do some kind of semi-classical limit, have a big system. But okay, so nothing happens, like the points, for example, the resonances, they don't move out of this line. They remain on this line. They just become denser and denser. And also in the continuum, there are more and more points, and it is not seen in this figure. So, okay, so now some examples and some first results. So in the first row, I have just like 6 tunneling potentials. So it's a simple Gaussian shape. Then this is a Gaussian, but with flat maximum. Then this symmetric double barrier potential. Then some more complicated potentials. And then even this potential with the part with the bound states. And these are the color plots, contour plots for the real part of the level density and imaginary part of the level density. And so, first of all, what I should stress is that that because of this Lorentzian shape of the or Lorentzian contribution from each of the resonance. So you see that it can be interpreted as like each resonance can be interpreted as a dipole in a two-dimensional plane, and the level density can be identified with something like electrostatic potential in a two-dimensional plane. The dipoles are oriented in the real, for the real part of the level density, they are like vertically oriented. For the imaginary part, they are horizontally oriented. So now you see very many like interesting things. Like for example, in this third column, there is this like well inside the barriers. So one can expect something like quasi-bound states, and you indeed observe the quasi-bound states here. So these are quasi-bound states that have like the imaginary part, the width is very small, but still it's non-zero. So these states have a non-zero imaginary part, but the part is very small. They are the decay width is very narrow, and so on. So the other thing is that, okay, we will be focusing from now on mostly on the real axis, on the real on the level density, but just for real energy, but for the real and imaginary part, for both parts, but only on these lines. And you can immediately see, for example, here again on the third column, in the third column, that the level density is somehow enhanced in the near the local maximum, which is this point. And there may be some sudden change near this local minimum of the tunneling potential, which is this point. So, but this I will discuss in more detail later. So this is just, okay, one can say it's a nice figure, one can use it as a tool to understand better this kind of potentials and tunneling, but what is it good for? So this level density, this complex level density, what can it be used to used for? So the first thing that I would like to show you is that this extended, this complex level density contains the whole information about the behavior of the transmitted wave. So it can be used as, so you know that the same is true for scattering matrix. It can be used to describe the scattering process. And you need just the extended level density, because it allows you to calculate the transmission amplitude, so which is the transmission probability and the corresponding phase. So this is actually the just to justify my claim. So you have so this formula given here was already known. So this phi is a phase shift, and if you take the first derivative with respect to energy of this phase shift, you get the real part of the level density in the continuum, introduced in the way that was introduced. So now let's look at the complex extension. So now let's look at the so now this delta, this capital delta, means that this quantity is already complex, so it can have real and complex values, but I focus on the cases where the argument, the energy, is simply real. So one can immediately see that you can it can be written in this form, expressed in this form. So you have the real part, which is the same line here, but you have also the imaginary part here. And so the imaginary part is actually connected to the transmission probability. So here is an example. So you can actually take the level density. So you know this quantity and you can integrate it and get the phase shift and the transmission probability, which is given here for this complicated type of potential. So the phase shift is given by the real part of this complex phi, and the transmission probability is given by the imaginary part. So here I plot the logarithm because you see that actually maybe I think there is a minus missing here, because you see that the transmission probability is very small when you are quite low, when you have to penetrate through the whole barrier. So so the conclusion from this part is that the transmission probability and phase shift can be obtained from the level density, from the complex level density itself. So now another connection. And so now let's move to the tunneling time. So one definition, there are several possible definitions of the tunneling time. So one is called Eisenbud-Vigner time shift, and it is defined via this formula. So this delta t is the time shift, and again you have the phase shift of the transmitted particle. So immediately using the formula from the previous slide, you can connect this Eisenbud-Vigner time shift to the level density. Let's make a complex extension of this quantity. So you can write actually something like this complex time shift as you can split it in a real part and imaginary part. And now let's try to find a completely different way how to calculate this time shift. So the real part of the time shift you can calculate as using the WKB formula approximation like this. So this is just a time that the particle spent in all the classically allowed regions, and this part, subtracted part, is connected with the free part in order to get rid of the infinities. So now I have a particle in a box from A to B. I can increase the size of the box because I subtract this part, and this time will remain finite. And now there is this bar over this time because this is a semi-classical calculation. So actually this is valid like this. Here you get a smooth function, while in the case calculated from the level density, you get something that won't be smooth. So in order to compare these two quantities, you have to perform some smoothing in the level density. So it can be done in several ways. One of the ways is just make some Gaussian smoothing of the level density. Okay, so this is about the real part of this time shift, and the imaginary part of the time shift you can calculate in a dual way. So you take the times that the particle spends inside the barriers. So you have to change the sign here to get a real quantity, and this is this is the instanton-like approach to the tunneling problem connected with the Wick rotation. It was introduced by Coleman like a couple of years ago. So we have these two quantities, and now, okay, now we would like to see whether there is some connection between them and what is the interpretation now. This is a crucial point because we come to the ground of, let's say, semi-classical description of quantum tunneling. So quantum, it's quite a contradiction. No? So semi-classical description of quantum tunneling. Quantum tunneling is a purely quantum effect, but now we want to, and we will come to some kind of interpretation or way how to describe this effect or understand this effect from this classical point of view. So I will just briefly talk a little about complex classical dynamics. So now we are in the framework of classical physics, and so the classical canonical coordinates are real, time is real, but we can extend them into complex domain, which is quite trivial task actually, but then you have to interpret or use these results carefully. So you can do this kind of extension. So then instead of a real Hamiltonian, you get a complex Hamiltonian that looks like this. Then you have a complex time. So you have to parameterize a curve in a complex time, in a complex plane, as some parameter that I denote S, which is a real parameter. So then the trajectory would be given by functions depending on S, but you will have also time, that your time will also depend on this variable S. So then S would be some kind of proper time of the system. Then the Hamiltonian equations look like this. The problem now is that this function, this like complex Hamiltonian, can explicitly or may explicitly depend on the time parameterizing variable S. So one has to be careful here. But okay, so there is a way how to choose a special parameterization in order to get rid of this problem. But okay, so you have a lot of freedom how to parameterize this, and this complex extension of classical dynamics is some nice mathematical tool. For example, if you calculate the connecting formulae in WKB approximation, so one of the way is that you know that when you want to cross the turning point, the WKB diverges there. So one way to connect the part in the forbidden and in the allowed regions is to go into the complex plane, complex coordinate. The other way is to connect it to approximate the potential here by a linear potential and use exact solution of the linear potential. But okay, so this is like a good, nice mathematical tool using complex coordinates to derive something that is valid also in the real for the real coordinates for the real system. So there is another completely separated but nice field, and it's a study of non-Hermitian PT symmetric Hamiltonians. This field has been introduced by Karl Bender, and so he started studying like quantum non-Hermitian PT symmetric systems. But then, okay, a nice extension or nice way is to go also into the classical physics and study the behavior of such systems in classical mechanics, and the behavior is highly unintuitive. So this is just a double well potential, but in a complex domain. So the energy is complex and the trajectories look like this. But I don't want to go into detail. I would just show that where this complex classical dynamics is used. So another example is the one that I mentioned with instanton solution, is the decay of false vacuum from the early periods of our universe. This work has been elaborated by Coleman. And okay, so there's also this theory that during the Big Bang, the time actually is, if you consider that the time is imaginary at the point of Big Bang, so then there is no singularity there. So actually this is Stephen Hawking works or was working in this field, and he showed that when you introduce the complex time, so then there are no boundaries in the description of the whole universe, like including the time direction, the time coordinate. So this is also another or one of the examples of complex extensions of classical physics. But okay, so now let's get to something more trivial. So let's go back to our tunneling problem, and let's choose a special parametrization. So the parametrization is the following. So the coordinate at each time is real. At each moment, the coordinate is real. The momentum switches between real and purely imaginary values when the real values we have in the classical allowed regions and imaginary in the forbidden regions. And then the time is real in the allowed regions, and it's pure imaginary in the complex region. So if you consider this kind of tunneling trajectory through this multi-barrier potential, so the time would be parameterized like this. So you have first the real motion in this first allowed region, then you have to tunnel through this first barrier, so you get pure imaginary component of the time. Then you are again in the real in the allowed region, so we have real time and so on and so forth. So in this way you can parameterize the tunneling classically. Okay, you have to introduce this kind of complex variables, especially the complex time, but you can formally describe tunneling classically. And if you do it like this, so then you can identify the time in the classical allowed region with this WKB formula, and in the forbidden with this like inverted or dual WKB formula. So for this particular potential, the tunneling scheme is the following. So this is the real value of time, this is the imaginary value of time, and this S is this proper time. So you see that the coordinate is real all the time because the imaginary part is 0, and the momentum is real in the allowed region, and then it is imaginary in the during the tunneling. So now, okay, so now we have some description, we have some interpretation of this formula. So this is formula that comes from the quantum considerations, but we can interpret it in the like from a classical point of view. So now the final thing is the connection with ESQPTs. So that's why we are here. We want to study ESQPTs. So we want to know what happens at the stationary points of this potential. So how the stationary points influence the time, the level density, and all these quantities. So this actually can be calculated in the very same way as in the classical, as for bound states. So you can expand the potential in the vicinity of the stationary point into some like locally into some quadratic or into high order function if the potential is flatter than quadratic, and you can integrate it and you can come to an expression of for the level density. So for the real part of the level density, it looks exactly as it would look for the level density of bound states. So if you have a local minimum of the potential, which means a bottom of some well between barriers, you may expect a jump in the level density when you increase energy and when this minimum appears. And if you approach the local maximum of a barrier or a global maximum of a barrier, you expect, and indeed you would observe this logarithmic divergence of the level density. And then you can perform the same semi-classical calculation for degenerate stationary points, which means of points that have flatter maximum or minimum. The stationary point is flatter than quadratic, and you get some little different formulas. But now what is an important contribution is that you can calculate the same for the imaginary part of the level density. And it appears that for the imaginary part, it is the same, but for inverted potential. So if you take your tunneling potential and you put it upside down, so the minima become maxima and vice versa. So then you would expect, using this derivation, that the local minimum of the potential actually induces this logarithmic divergence, and the local maximum induces a jump. So there is this minus, because now you have to, like formally, you have to turn upside down also the kinetic term. So you have a maximum, like if you use this classification of the non-degenerate stationary points using the index of the stationary point. So actually the index here would be 1, but the index here would be 2, because you would have like maximum both in kinetic term and in the potential. And also you can calculate it for higher for flatter stationary points. So this is so there is an expected dual structure of the real and imaginary part of the level density. And now so now let's look at the results. So now we have two very different calculations. One is semi-classical, like via this WKB formula, so just calculating the time that the trajectory spends either in the kinematically allowed regions or in the kinematically forbidden regions. And then you have the quantum calculation via this quantum continuum level density. And we can compare both results numerically, and it's shown in these 6 panels for the 6 different potentials. And you see that the correspondence is perfect. So you see that the dashed line is the semi-classical calculation. It's the time actually, and the solid line is the quantum calculation. So in the quantum case, the system is like finite. We are not in the semi-classical limit. That's why we see some precursors of the ESQPT singularities here, but the precursors are quite well pronounced, and far from the precursors, the lines just coincide. So this is a nice like numerical proof that there is indeed a strong connection between the quantum interpretation and the classical one, and also it supports this kind of semi-classical view of the quantum tunneling, that you can like interpret the tunneling by the parameterization, complex parameterization that I showed a couple of slides before. So you see here, so there are examples even for these complicated tunneling potentials. There is also, it also works actually, this approach when you have a system with bound states. So you see that you have to extend the definition a little to get the imaginary part of the level density for negative energies, for bound in the region of bound states, but you can do it, and you see that, okay, so there is this local minimum, there is this global minimum of this potential, and this is already in the bound states region, and you see that there is a divergence of the imaginary part of the level density. So I think I have come to the summary and conclusions. So very briefly, the summary, where I would like to show you the algorithms, the steps that I followed during this seminar. So I started with a tunneling one-dimensional system, so a system with 1 degree of freedom. So then I calculated the complex level density, which has to be introduced in some a little different way than the level density for bound states. Complex level density, so the real part and the imaginary part, they look like this. So then I restricted myself just to the real axis in these graphs. From the real level density, sorry, for the level density on the real axis, you can calculate everything about the scattering process, so like the phase shift or transmission probability, but you can also perform some kind of smoothing, or you can go closer towards the semi-classical limit, increasing the system size, and you can calculate the Eisenbud-Vigner time, or you can take the same tunneling potential and calculate the semi-classical time, and you arrive to the same curves, and then you can interpret this graph as a complex, in terms of complex classical dynamics, as a like a classical description of the quantum tunneling. So this is the summary of the procedure. So now a little the main points in the conclusion. So these 7 points are, so the first point is that we can extend the level density into the continuum. The second part is that we can actually calculate or connect the smooth part of the level density in on the real axis, but both real and imaginary component, and we can calculate them semi-classically just from the time that the classical trajectory spends in the allowed and forbidden regions of the potential. Then this allows one to formulate a semi-classical interpretation of the tunneling problems. Then you can observe the same kind of ESQPT structure of non-analyticities in the level density. And as we already know from the bound states, but here you see the dual structure also in the imaginary part of the level density. Now the open question is what happens when the system has more degrees of freedom. So as we know, if a bound system has f degrees of freedom, then the singularities in the level density appear in the f minus first derivative of the level density. So I would guess that we can observe the same even in the continuum, but this is an open question. And okay, so now for experimentalists, so these singularities actually in the level density can be subject of some experimental studies, of some tunneling experiments. So that's all from myself, and I would like to thank you all for your attention, and I am prepared to answer your questions. Thank you.
Okay, okay, Pavel, very nice talk. A very nice talk about the subject, which is not easy because as this is, as I mentioned in the beginning, this is completely brand new, like extending ESQPTs to the continuum. So you have to set up the full formal from the beginning. I think my own that the agencies is made an effort to make it pedagogical and for us to try to follow you. But so if somebody has any question, remark, suggestion for Pavel, so you can raise your hand or just unmute and ask Pavel.
I have a question, Juan Diego from Regensburg. Hi, Pavel. Thanks a lot for the.
Hi, Juan Diego.
Very nice. So you choose a specific way of complexify your classical dynamics, meaning which is very natural, no, for tunneling problems. You let the momentum get imaginary, and the coordinate you keep real, let's say. Mm-hmm. But let's say if I have a Hamiltonian which are more complicated with a more complicated structure, and then not only p squared plus potential, but something more complicated, a general Hamiltonian depending on Q and P, then the stationary points of this Hamiltonian in the complex plane are incredibly rich. This we know. The moment you complexify things, do you think that the stationary points in the complex XP plane eventually have some effect on the dynamics? Can be observed? It would be something like a complex, like a ESQPT coming from a complex fixed point in phase space. Do you think this makes sense to pose that question at all? First of all.
Okay, I think it's a very good question, but actually I don't know, because okay, so the first thing is one thing that I can comment on is that, okay, you can have a complicated Hamiltonian, but still a real Hamiltonian with the real stationary points that can appear in some non-trivial, for some non-trivial values of P and Q of coordinates and momenta.
And this will produce an SQPT for sure. I mean,
this will induce an ESQPT, and this, okay, if you at least if you calculate the semi-classical this delta T, what I called using WKB formula, so there you would see these kind of singularities. They will be connected. It doesn't actually matter. So okay, so this is so I think yes, in this case you would see probably the same thing. Okay, then there is this the whole interpretation can be more difficult, because then I think the tunneling, okay, the dynamics, the continuum dynamics would be, I don't know, the plane waves there, for example, the incoming wave and outgoing wave. It requires this splitting of the Hamiltonian into kinetic and potential energy. So there, actually, I don't know how to interpret it, how to treat this problem, but this is, I think, an interesting open question that we haven't thought so far.
Thank you very much again for everything, man. Thank you.
Thank you.
Okay, Ami raised his hand, so next question is Ami's.
Mm-hmm.
Yeah, okay. Thank you very much. I have two questions. One, this dual relation that you show between the imaginary part and the real part, is that suggesting of some kind of dispersion relation, you know, that you can write one in terms of the other?
Okay, so I think I don't think so, because both of them are connected with like different okay, so it's like a real and imaginary part of one quantity. So actually, if you have this level density or the complex phase shift, so it's one quantity, and you get both the real and imaginary part. So the dual structure is in the real and imaginary part of one quantity. So in this sense, yes, but I don't see now any connection like from the real okay, I don't see that there could be some real function, and you can map this one function into the real and imaginary part of the level density or so on, and see this dual structure, but in one real quantity. So what I showed is a complex level density, and okay, it's one quantity that has this some dual behavior in the real and imaginary component.
Okay, and a second question, I mean, you mentioned in passing this PT symmetric Hamiltonian. I mean, I think you mentioned the work of Bender. Can you say more on that? Because there is a lot of group theory that goes into that. Yeah, this one.
Yeah, okay, I can't say much of this, because I think this is just an example. It's not related, as far as I understand it, it's not related to the case, to the parameterization of the complex trajectory that I used, that we are using. But this is just an example that one can study the classical dynamics, and actually like one of the conclusions of the Karl Bender and his collaborators is that if you have that, okay, so there are some poles in the complex plane, and so the like PT symmetric dynamics correspond to the trajectories, classical trajectories that are that connect these poles and that are periodic in some sense, while the PT non-symmetric evolution or PT non-symmetric dynamics is connected with trajectories that are not periodic. So, for example, this example that I show, is just an illustration, is not a PT symmetric case. But in these two papers, the authors show that if you have a PT symmetric case, then you have like nice simple trajectories connecting the poles in this complex coordinate plane.
Yeah, but I think they show that you don't need the Hamiltonian to be Hermitian in order to give real eigenvalues. It only has to be a PT symmetric.
Yeah, exactly. Okay. Yeah. So this is it. Yeah, thank you. This is it. So the Hamiltonian is PT symmetric. So it can be non-Hermitian but PT symmetric. Then it has a real spectrum. And if you take the same parameters, the same Hamiltonian in the classical physics, so then the PT symmetric case corresponds to the simple periodic trajectories in this complex classical dynamics. And if the system, because you can, they show in the quantum case that one Hamiltonian, so you can choose some part of the complex plane where the same Hamiltonian is PT symmetric and has real spectrum, and it doesn't have real spectrum. So actually, I am not an expert in this field, but okay, you are right that the Hamiltonian, what they study and what they propose is that you can have the PT symmetric non-Hermitian Hamiltonian with a real spectrum, and this is actually quite an extensive area of research. This is useful for some this gain loss kind of system where you have some open system with some equilibrium of incoming and outgoing energy, and you so the system has some real spectrum, but it is not Hermitian, so the energy is not conserved.
Yes, thank you.
Thank you. There is another hand raised. It is Jorge Hirsch, so it's his turn.
Okay.
Hello, Jorge.
Pavel, yes, it is very nice to see you, and really, I really appreciate, as Kuro said, the pedagogical approach you had for this talk, because you guided us through a very complicated panorama, but with many moments of rest in very specific examples which help us to go with you. And I am really amazed by these complex classical dynamics, because it seems to give some kind of relation or kind of intuition about these quantum processes. But for example, here you have in the semi-classical modeling of the tunneling, you have time in which the particle is inside the barrier. Do you think this has some meaning related with the more sophisticated quantum description, or this is just an artifact of this semi-classical description?
So I think this is still an open question. So in our studies, this framework, this image of complex dynamics is just like a tool or way that helps us interpret this this formula for the Eisenbud time or extended Eisenbud Vigner time shift. But okay, this is really still question under study. What happens when the particle tunnels? So actually, okay, so you cannot see the particle inside because you cannot enter the barrier. So you can put the particle here, or I think people do it in the other way. So they put the particle in the well and they wait outside and measure the time of appearing of the particle. But okay, so you see the time is in this interpretation, in this model, let's say the time is imaginary inside. So okay, I think that I cannot give you any like more detailed or more profound answer, but the whole point is that this nicely models the situation, but I cannot say more about the time or about the behavior of the particle inside the barrier. So I'm afraid that I probably haven't answered your question, but thanks anyway for it.
It is very, very interesting. And is there any, do you know, for me it is very new, this idea, but are there different attempts to map the kind of the quantum dynamics to the classical dynamics with, I imagine, with complex component? This is more general than just scattering?
Okay, so this is one of the most trivial parameterization. So there are many studies, I think, mostly done in the area of quantum field theory, where you can like so people what they study, they take the Feynman integral and they perform the big rotation there, and they study the dynamics of this like in this framework. But okay, I am not familiar with this, so I cannot give you some like interesting answer. But okay, so this is actually this trajectory in the complex time of this parameterization is just one possible. So there are, and I think the authors in these papers, they consider also a little more complicated parameterizations, but that's all I know about it. Maybe I don't know whether Pavel Cejnar is connected, because he is very he knows a lot details also about this kind of studies, so maybe he can connect on this, but I cannot.
Thank you.
Thank you, Jorge.
Thank you, Jorge.
Okay, I am connected, but but I think you said it very well. I mean, actually, this was certainly, there is a plenty of possibilities that you have if you have this complex plane of time. You can take any curve in that plane, and each curve will generate a different classical dynamics, basically, because the generalized Hamilton equations depend on this curve somehow. But we think that probably this simplest possibility that was proposed in those papers that Pavel cited somehow captures the most essential part of the process, of the tunneling process. So it's kind of I think it's somehow really close to some semi-classical treatment of the tunneling process, which seems like an oxymoron, because tunneling has no classical limit, but it has in terms of this complex time and in terms of these complex trajectories. But I'm also a beginner in this. I don't know much, really.
Okay, thank you, Pavel. So let's see if there is any other question for our speaker today. I just have a very quick question, and because it's already quite late, it's out of curiosity, because you mentioned from the very beginning, like putting your potential into a box and then enlarging the radius of the box, looking for solutions. But when working on scattering problems, there are other options, and then, for example, you can use some discrete basis, like a harmonic oscillator, let's say, and then you increase the dimension of your harmonic oscillator, and then you can see, for example, following the positive energy eigenvalues, check where there are resonances or not. Is it possible to perform this complex scaling and from this other perspective, using something like a harmonic oscillator basis instead of a square well?
Yeah, I think so. I think it's just so we use the box because it's one way to choose the eigenbasis actually. So so I don't know. I have to think about the complex scaling method, but the complex scaling method, in fact, is not a necessary component. So this procedure works in. You can use any other way to calculate the complex spectrum, and I didn't say it here, but you can actually all the calculations, all the results you get, because we focus only on the real axis here. So all the calculations are valid also when the complex scaling angle is 0. So when you don't see, when you don't reveal any of the resonances. But the nice thing here is that you reveal the resonances, and so that you see that the behavior on the real axis is given mostly by the resonances themselves. You see that immediately in this point, for example, that there is an increase in the level density. The color is little more, it's a little darker here. So you don't have to care much about the rotated states, about the continuum. But so everything is valid when the angle is 0. So when all the states actually are on the real axis, it works there. And in that case, you can definitely use whichever basis you want is suitable for your problem.
And then when you showed the precursors of the ESQPT together with the semi-classical result, then these precursors they depend on some way on the dimension on your basis. That means in your radius of the box, or what way can you make these precursors tend towards the classical values? What magnitude you increase?
These results are completely independent on the size of the box. So the box is so huge that really you just cover, it's like the potential, all the relevant values of the potential are well within the box. So it is independent of the box size, but it depends on this size parameter, which in this case is connected. So one can tune either the mass of the particle or the Planck constant. So I showed this. I just remind you. I showed you this kind of graph here.
The K parameter.
So this kappa parameter.
Kappa parameter. Yes.
So you can tune this, but if you have a many-body system, like I don't know how to extend Vibron model or any kind of Lipkin model to continuum, but if you had this kind of system, then this is the same as increasing the size parameter n. When you increase n or this kappa, your curves in these graphs would tend towards the semi-classical curves given by the WKB formula.
Okay, thank you very much, Pavel. Thank you again for the very nice seminar, and thank you to the audience too for attending once again to our ESQPT 2021 seminar series. So next week it will be Armando Relaño, the chosen speaker. Okay, and I will tell this again on next week, but for those of you that are still here, patient ones, we are also waiting for proposals of people that are willing to give seminar on ESQPT related research. Okay, so thank you for everybody, and I hope that you stay well and safe till next Friday. Okay.